Continuing on with the physics problems, this one is very similar to the last one that we just covered. This one asks, how long does it take for an object to fall from a height of 160 feet? So this time we're asking a slightly different variation on that question. We have the ball, and we want to know how much time it takes to go all the way down. So if we're trying to find time, we can presume that t is the variable that we do not know. But do we know the others? We start from a height of 160 feet, so we can say, okay, our initial height is 160 feet. The object is falling. It doesn't say anything about it being thrown upwards or sideways or anything like that. It just was dropped, so in that case it has an initial velocity of 0, just like the last one. And this last one here, h of t, if t is unknown, then we have to assume that we know h of t. And what we're trying to solve there is we're saying when it hits the ground. So we're saying when h of t equals 0, how much time has passed. So we're going to set this equal to 0 feet, because we want to know how much time passes from when we're at 160 feet until we get down to 0. So popping this into our equation, we have 0 here for h of t equal to negative 16 t squared, t is unknown, so we leave it as t, plus 0t, because that's our initial velocity, plus 160, our initial height, just following the equation up here. At this point, we just go forward and solve it. Our middle term with 0 drops out. We can move our negative 16 to the other side, negative 16t squared. Divide both sides by 16, and take the square root of both sides in order to get it by itself. So in physics problems, typically you don't want to leave things as roots because unlike mathematicians who want to know the exact answers, the physics people are looking for more of a real-world solution that you can understand. So something like plus or minus 3.2 seconds is much easier to understand than the square root of 10 seconds. However, negative 3.2 seconds doesn't really make any sense in the context of a physics problem like this. How much time has passed? It's hard for negative time to pass. So for this, we're going to throw out that one answer and keep only the 3.2 seconds being the positive solution that we got. So the amount of time it would take for this ball to drop 160 feet is 3.2 seconds. Again, another very similar problem. An object is thrown upwards at a velocity of 10 feet per second from the top of a building. When will it hit the ground? So this time, the ball started at the top of the building, was thrown upwards, and then came down. In the case of this, we still have an initial height of 160 because it was thrown from the top of the building that's 160 feet in the air, which is right up here. We still want to know when it hits the ground, so we still want to know when h of t is equal to 0. We're still looking for when it will hit the ground, so we're looking for t, so we don't know t. And v0, our initial velocity here, it says it was thrown upwards in the positive direction. Upwards usually is positive in physics problems. Upwards at a velocity of 10 feet per second. So we're going to use 10 feet per second as our initial velocity. Again, you pop these into the equation. H of t is 0. T stays as t in a couple places here. Our initial velocity of 10, this time we have a middle term, it doesn't drop out. And our 160 feet gets stacked on here at the end. Because this is a quadratic equation with t in multiple places, it doesn't solve as easily as the last one did, but we can use the quadratic formula to help us out here. So let's identify our coefficients. Our a term, the coefficient of the squared term here, is negative 16. Coefficient of t to the first, 10. Coefficient, or the constant by itself, is 160. Pop that into the quadratic equation, and we're given the answers of t equals negative 29 or t equals 3.5. Again, I skipped over the calculation step here because the key aspect that's new to you for these types of problem is learning how to set them up. So once we get into that stage, you can refer back to your notes on the quadratic equation or any other technique you want to use to solve this in order to finish off the problem. So t equals negative 2.9 seconds here because we're looking at time, or 3.5 seconds. Since we, again, are not going to be using negative time, we're going to just say that our final answer is 3.5 seconds. If you start at the top of the building, threw it upwards at that speed of 10 feet per second, and let it fall back down on its own with gravity, it's going to come down in 3.5 seconds. Now let's look at something a little bit more complicated. I threw a baseball straight up in the air. That means that I'm standing on the ground, and I threw the baseball above my head. I caught that ball 3 seconds later. So I threw up the ball, counted 1 1,000, 2 1,000, 3 1,000, landed back in my hand at the same height that I released it. What was the upward velocity of my throw? So how hard did I have to throw it in the air in order for it to stay up there for 3 full seconds? Same equation as the last problems that we did with the ball on the building. We know that if we have 3 seconds in the air, our t is going to be equal to 3 seconds. Our initial velocity is what we're trying to solve for. What was the upward velocity of my throw? What was my initial velocity when I released the ball out of my hand? So we don't know that. H of t and h naught, the height at the final time and the height at the starting time, are going to be the same, because what the problem says is that I threw the baseball up in the air, so wherever I'm standing, let's say I'm standing on the ground, which we'll call 0, I then caught it in the same place. So wherever I was standing when I threw the ball is where the ball returned to. So we're going to use 0 for both of those. If we pop that into our equation now, we have h of t equal to 0, our negative 16, which is our gravity constant, times 3 squared, plus 3, because t equals 3 here. So we're going to plus 3 times our initial velocity, plus that initial height, which we said was 0. Go ahead and start solving this, and we only have one variable in the equation, and it's to the first power, so it's a fairly straightforward algebra problem to solve it from here. Our 0 drops out, and this simplifies down to negative 144. Shift it to the other side of the equation by adding 144 to both sides, and then divide everything through by 3. And you're left with v naught equals 36, which means that in the context of this problem, the speed that I threw the ball in order to make it stay up for 3 full seconds was 36 feet per second. If I were to draw the height versus time graph of this, just to give you an idea of how this works, I throw it up at 0 seconds, and it lands back in my glove at 3 seconds. And in the meantime, it goes up in the air, kind of slows down, turns around, and then comes crashing back to me. So it forms a parabola shape as far as the height versus time. The position now, we said I threw it straight up. So it just went straight up in the air and came back down. But if you're comparing this versus the time elapsed since I threw the ball, 1 second has passed. It's a little bit higher. 2 seconds has passed. It's already coming down. 3 seconds has passed. It's back on, in my glove, not above the ground. And now, last example, we're going to take that type of problem and extend it one step further to see if things are moving horizontally also. I shot a basketball 20 feet away from the hoop. I released the ball 6 feet in the air, and it passed through the rim 10 feet in the air. So as a basketball player, I'm about 6 feet tall. We'll round it and say that. And that's where I released my ball. And the rim, which is 10 feet up, is where the ball was when it landed. There was 2 seconds of hang time, which means that from the time I shot it, 1 1,000, 2 1,000, then it went through the rim. What was the upward velocity of my shot? And what was the horizontal velocity of my shot? You'll understand why I'm breaking this up into 2 questions in a little bit. But for now, just know that when you're trying to figure out how fast something started out moving, you can't just very easily say, oh, well, how hard did I shoot it and in what direction? It's easier to break it up into how much in the vertical component and how much in the horizontal component. So let's start with the vertical component, because that's what we've been doing in the last few problems. And for the vertical component, we use that same equation we've been using. Gravity is pushing straight down on us. We have an initial velocity and we have an initial height. So the initial height, I'm 6 feet tall, that's where the ball was released. That's going to be 6 feet. The final height is when it went through the rim. That's 10 feet in the air. So our final height, our h of t, is going to be 10. There were 2 seconds of hang time. The ball was in the air for 2 seconds. So our t, our time spent traveling, is going to be 2 seconds. And our initial velocity is what we're trying to calculate. So that's going to be unknown. So we're going to pop this all into the equation just like we've been doing. We have 10 here for h of t. Negative 16 is our gravity constant, so we'll leave that there, times 2 squared, because that's our value of t, plus 2, since it's our value of t again, times that initial velocity, plus 6, which is how many feet we started up in the air. There's only one variable here that we're solving for, and everything else is constant, so it's just an algebra problem like the last one. We can simplify this term here down to negative 64. This stays 2v naught and this stays 6. Collapse our constants all together on the left side by adding 64 to both sides and subtracting 6 from both sides, and we're left with 68 is equal to our lone 2v that's still here. And when you solve for v naught, you're left with 34. So the initial velocity in the vertical direction is 34 feet per second. That means that when I took my shot, there's 34 feet per second of initial velocity being pushed upwards on that basketball. Now it asks, what was the horizontal velocity of my shot? Until you take a physics course, you're probably not going to understand in depth exactly how all of this works. So I'm going to ask you to take some of this on faith here. Just trust me that it does in fact work. But there's no forces acting on something when it's traveling in the horizontal direction. When you throw things up, there's gravity pushing back down on it. But when you're walking side to side, there's not any major forces acting on you. If you want to get technical, things like air resistance come into play, but it's such a small effect that we're going to leave that out for now and still get a fairly accurate calculation. So gravity is the big force that we have to deal with, and that only pushes up and down in the vertical direction. So that means in the horizontal direction, we're left here with an equation v equals d over t, which means our velocity, v, is equal to the distance traveled over the amount of time spent traveling. And this makes sense if you're in a car, for example, and you travel 5 miles and it takes you 1 hour to do so, you're traveling then 5 miles per hour. In the case of this, we're going to use feet per second. So d, our distance traveled, is 20 feet because I shot a basketball from 20 feet away. The t here, still 2 seconds, is 2. So what we're saying in this case is that it took the ball traveled 10 feet for each second, which means that in 2 seconds it traveled 20 feet all the way from where I was standing to the basketball hoop. And this is the type of equation that, if you were ever given a problem like this, would be given to you. We're not going to see this level of difficulty on the tests or quizzes, but in the project we'll be doing, this is something that will come up. So our horizontal velocity is 10 feet per second.